Welcome to Educator.com. In this lesson, we're going to work on solving a system of equations using the substitution method. So, really what we want to focus on is how we use this substitution method in order to find solutions, and I'll really walk you through that process. We'll also keep in mind that since sometimes there is no solution or there's an infinite amount of solutions, how we can recognize those cases when using the substitution method. Alright, so recall the reason why we need more methods for solving a system is that when we use the graphing method, that you really have to be very accurate in order for that method to work. And if your lines are a little bit wavy or you don't make them just right, then you may not find the solution of that system. Since accuracy is such a problem, that's why we're going to focus more on those algebraic methods. So really, how can we manipulate the system in such a way so that it gives us a solution? Now, two of these methods of our algebraic methods are substitution and elimination. In this lesson, we'll really focus on the substitution and then look at elimination in the next one. So let's see how the substitution method works. In the substitution method, what we first end up doing is taking one of our equations and solving it for one of the variables. Once we've taken one equation and we've solved it for a variable, we'll take that and substitute it into the other equation. Now what this will do is it will give us an entirely new equation with only one type of variable in it. And we'll end up solving for that one remaining variable that is in there. So we'll have half of our solution, but since we're looking for a system and we need an x and a y coordinate, then we'll end up using back substitution to find the rest of our solution. So we'll take what we have found and end up substituting back into one of the original equations. This will help us find the other variable. Now, as long as everything works out good, it should be our solution, but it's not a bad idea to just take that and check it in the original system. If you do make a mistake, sometimes you won't catch it, so plugging it back into the original system, always a good idea. Let's walk through this substitution method using the following example. Here I have negative x plus 3y is equal to 10, and 2x plus 8y is equal to negative 6. So I want to start solving for at least one of the variables in one of the equations. And I have lots of different choices that I can do. I can solve for x over here, I can solve for y in the first one, or you can even pick on the second equation a little bit and solve for its x or solve for its y. It doesn't really matter which one you solve for, just pick a variable and go ahead and solve for it. I'm going to choose x in the first equation. It looks like it'll be one of the easier ones to get all by itself. So what I'll do is solve for x, and I'm moving everything to the other side. So I'm subtracting a 3y on both sides. Now it's almost all by itself, but looks like I'll have to multiply by a negative 1 to continue on from there. So multiplying through by a negative 1, I'd end up with x is equal to 3y minus 10. Now this entire thing right here is equal to x. So where the substitution part of the substitution method happens is I will take the x in the other equation and replace it with what it's equal to, the 3y minus 10. I'm going to leave lots of room for this, so you can see what it's going to turn that second equation into. So instead of writing x, I'm going to write 3y minus 10. So I've taken that second equation, substituted in those values, and notice how in this new equation we created, it only has y. Since this new equation only has y's in it, we'll be able to solve for y and be able to figure out what that is. We still have a little bit of work to do. Of course, we'll have to simplify it and combine terms, but we'll definitely be able to solve for that y. So let's give it a shot. I'm going to distribute through by my 2, end up with a 6y minus 20 plus 8y equals a negative 6. Okay, not bad. Now let's go ahead and combine our y terms. So 6 plus 8 is a 14y. And then let's go ahead and add 20 to both sides. So 14y, negative 6 plus 20 is 14. Finally, divide both sides by 14 and get y equals 1. So it looks like I have a solution, but remember this is only half of our solution. We still need to figure out what x is. Well, at this point, now that we know what y is, I can again substitute it back into one of my equations and figure that out. So let's do that. So negative x plus 3, and I'll put in what y is equal to, a 1. And now I'll end up solving this equation for x. So negative x plus 3 is equal to 10. All right? So I'm going to subtract 3 from both sides. Okay, almost done. Now I'll go ahead and multiply both sides by a negative 1 and get x is equal to a negative 7. All right, so now I have both halves of my solution. So the x is written first, so negative 7, and y is written second. So my solution is negative 7, 1. Now if I'm looking at that and I'm curious if it really is the solution or not, it's not a bad idea to just take it and plug it back into the original. Let's see how that works out. So negative, my value for x is negative 7, plus 3, and my value for y is 1. Does that really equal 10? Let's find out. So a negative 7 would be positive 7 plus 3. Does that equal to 10? Sure enough, 7 plus 3 is 10. So that works out in the first equation. All right, now let's do the same with the second one. 2 times a negative 7 plus 8 times 1. Is that equal to a negative 6? Well, let's find out. So negative 14 plus 8. Sure enough, negative 6 is equal to negative 6, so it checks out in both equations, and I know that negative 7, 1 is my solution. So there is a lot of substitution, of course, in the substitution method, but it's not as bad as you'd think, and you do have some choices on what you solve for and where it goes. All right. So one thing that we saw when we were finding solutions graphically is that several things could happen. We might have one solution, we might have no solution, or we actually might have an infinite amount of solutions. Now, when we were looking at all of these graphically, it was pretty simple on figuring out which case we were at. We either looked at both of our lines and they actually crossed, and we said, oh, they have a solution. We could see if there was no solutions if the lines were parallel, and we could see that it was an infinite amount of solutions if they were the same line. But now that we're doing things more algebraically, we won't be able to visually see what case we're in. So how is it we figure out if it has no solution or an infinite amount of solutions? Well, it all depends on what values you get while going through that solving process. So if you go through the substitution method and you can actually find an x and y that work, then you know that it has a solution, and it has one solution. So nothing strange happens. If, however, you go through that substitution method and you end up creating a false statement, it means that there is actually no solution to the system. Now, if you do come across a false statement, what I always tell everyone is check your work first to make sure that you have made no mistakes. If all your work looks great and you still create a false statement, then you can be sure that it has no solution. Now, if you go through and you create a true statement, but you can't really see what your solution is, well, that's a good indication that the two lines are exactly the same and you have an infinite amount of solutions. Again, check your work with this one. But if all your work looks good, then you know that you have an infinite amount. So let's look at some examples like these ones and see how we can recognize what I mean by a false statement and what I mean by a true statement. We want to solve the following system. 5x minus 4y is equal to 9, and 3 minus 2y is equal to a negative x. So the first thing I need to do is solve for either x or y. It doesn't matter which one we choose. It looks like it might be a good idea to solve for x down here since it's almost all by itself anyway. We'll just go ahead and multiply everything through by a -1. So -3 plus 2y equals x. Okay? Now that we have what x is equal to, we'll substitute it into the first equation for that x. We'll leave lots of space and we'll just go ahead and put it in there. So -3 plus 2y. All right, we can see in this new equation it only has y's, so I need to work on getting them together and isolating them. So -15, that'd be from distributing through, plus 10y minus 4y equals 9. Okay, I have some like terms I can put together. 10y and -4. That would be 6y equals 9. Okay, not bad. Adding 15 to both sides. Let's see, plus 15, 24. Now dividing both sides by 6. I get that y is equal to 4. So we have half of our solution. Now let's figure out what the other half is by putting it back in one of the original equations. Now, I often have students ask me, wait, should you put it back in the original? After all, couldn't I just stick that y back in up here? And what I tell them is, yes, you could put it back into, say, this equation for y. But be very careful because that equation you've already manipulated in some sort of way. If you want to be sure that you're not making mistakes on top of the mistakes, take that and plug it into one of the original ones, something that you haven't messed around with too much. All right, so let's see. 3 minus 2, and we'll put the 4 in there. Now we'll take this and solve for x. So 3 minus 8 equals a -x. Let's see, 3 minus 8 would be a -5. And dividing both sides by a negative, I have that x is equal to 5. So now I have both halves of my solution. X is equal to 5. Y is equal to 4. So my solution is 5, 4. All right. Now, again, if you want to really make sure that that is the solution, feel free to plug it back into both equations and check it and make sure it works out. All right. In this next example, we'll see if we can solve this one using the substitution method. This is 4x minus 5y equals -11, and x plus 2y is equal to 7. All right, so let's see. What variable shall we solve for? Well, this x looks like it'd be nice and easy to get all alone, so let's do that one. We'll go ahead and say x is equal to a -2y plus 7. So I took the 2y and subtracted it from both sides. Now I'll take all of this and substitute it into the first one. This will give me 4 minus 5y equals -11. And I left a big open spot so I can drop what x is equal to in there. So 2y plus 7. Okay, looks good. All right, now I'm going to distribute through with my 4. So -8y plus 28. And I'm going to continue trying to solve for y. So let's see what I got here. -8 minus 5. Putting those together, I'd end up with a -13. Subtracting 28 from both sides, I'd end up with a -39. And looks like I can, finally do dividing both sides by -13 and getting that y is equal to a +3. So let's go ahead and take that and substitute it back into one of our original equations. Let's go ahead and put it here. So x plus 2 times y. Okay. Multiplying together the 2 and the 3 would be a 6. And then I'm left with x plus 6 is equal to 7. So subtracting 6 from both sides, x is equal to 1. So my solution for this one is x equals 1, y equals 3. Looks good. Now, in some systems, remember, we could have that situation of having no solution or an infinite amount of solutions. And sometimes when you're looking at an equation, it's really tough to tell whether you have that situation or not. Watch very carefully what happens with this one. So I'm going to start off like I did with the other examples. We really just want to take these and solve it for one of our variables. And I'm going to solve the first one for x, since that one looks like it'd be nice and easy to get isolated. So that would give me x, subtract a 2y from both sides, plus 4. Now that I have x isolated, let's substitute it into the second equation. So 3, leave lots of space, plus 6y equals 13, and we'll drop in negative 2y plus 4. All right. Now I only have y's in this new equation, so we'll continue solving it by getting y all by itself. Let's go ahead and distribute. So negative 6y plus 12 plus 6y equals 13. Now notice something interesting is happening here. Over here I have a negative 6y, and over here I have a positive 6y. And since they're like terms, I can put them together. But a negative 6 and a positive 6 would give me 0y. So they cancel each other out. Now, that means the only thing left is a 12 on the left and a 13 on the right. But that doesn't really make any sense. 12 is not equal to 13. So I'm going to write not true. Now, if you really check through back all of my steps, I didn't make any errors. I mean, I moved the negative 2y to the other side. That turned out okay. And I did my distribution fine. So I know my steps worked out, perfectly good. So what this statement is telling me at the very end, since it is not true, is that these two lines are actually parallel. There is no solution, and they do not cross. So watch out for these false statements that might come along the way, and they will help you recognize when a system does not have a solution. All right, one more system. This one is 2y is equal to 4x, and the other equation is 4x minus 2y is equal to 0. Let's take the first one and solve it for y, which we can easily do just by dividing both sides by 2. So y equals 2x. Okay, now that it's solved for y, let's go ahead and substitute that into the second equation. Interesting. Well, let's keep going. You can see that this is turning out a lot like the previous example, in that if I combine my x's together, since they're like terms, they're going to end up canceling each other out. This is slightly different, though, because after they do cancel out, all I get is 0 equals 0, which happens to be a true statement. 0 does equal 0. So again, let's check our work, make sure we did everything okay. So I divided both sides by 2, and that worked out good, and I combined my 2's together and canceled, so all my work looks great. So the fact that I have a true statement and all my steps were good means that what's really going on here is that the lines themselves are exactly the same line. In fact, we might even see that at the very beginning if we end up rewriting them. When I move, say, the 2y to the other side on the second equation, and then end up rearranging them, sure enough, they are exactly the same equation. So visually, these would be right on top of one another. So this tells us we have an infinite number of solutions. And everywhere on that line is a solution. So these more algebraic methods are definitely more accurate when it comes to finding solutions. You want to be very familiar and being able to go through them. Also be on the watch out for these two special cases. So if you get a false statement, then you know you have no solution. And if you get a true statement, then you know you have an infinite amount of solutions. Thank you for watching Educator.com.